Hello Chem students. I'm going to go over bond line formulas from chapter 1, hopefully a fairly short video. So let's take a look. We have certain ways of drawing structures that are very informative, but they take a lot of time. So if you look at this top structure, I can see all of the carbons and hydrogens. I don't draw out every hydrogen connection to the carbons, but I can see all of them that are there. I can tell this carbon doesn't have any hydrogens on it and no pi bonds. This structure right here is more informative, but takes a lot more time to draw. I timed myself on this one. It took 45 seconds to draw this structure. I've indicated the numbers here to help us figure out what are the hybridizations and the number of hydrogens and so forth. So we'll see on the next slide the bond line formula, where these will be harder to determine. So you'll have to have some little clues to do that. Okay, so let's take a look at the next slide. So the next slide, you'll notice there are no carbons drawn and there are no hydrogens drawn. And this is called a bond line formula. It's much more condensed, less information available to you, but much easier to draw and work with. So this is actually a very, very common way that organic chemists like to draw structures, and biochemists as well. So now, if we wanted to figure out how many hydrogens are on each carbon, we know that a carbon, say like carbon number 1 here, carbon 1 has 4 bonds, but I only see 3, and I just see 3 lines. So those are the bonds that are not to hydrogen. Any bonds to hydrogen are left out. So if you wanted to know how many hydrogens are there, you have to come to carbon's normal number of 4 and subtract the number of bonds that you see, and that would be the hydrogens that are present on that carbon. So in this case, we would have 4 minus 3. There would be 1 hydrogen here. Since there's 3 bonds between these 2 carbons, I know that the second and third bonds are pi bonds. Pi bonds use p orbitals, so those would not be involved in hybridization, leaving only an s and a p to hybridize. So this must be sp hybridized carbon, which also means that it is linear, which also means that it has 180 degree bond angles. So the missing hydrogen has to be 180 degrees opposite to number 2 over here. That would be a hydrogen sitting here. And if we went to carbon 2, we would see again 4 bonds. 4 minus 4 means 0, and there would be no hydrogens on this carbon. Still, it has a second and third pi bond, so it would also be sp. If we went to 3 as an example, we see a bend in the line. Every bend in the line is a carbon. Every end of a line on each end here is a carbon. Okay, so I have 2 lines shown, meaning 2 bonds to carbon. 4 minus 2 would be 2, so there's 2 hydrogens missing here. This would be a CH2. There are no pi bonds, so all the S and all the P's would be mixed together to be sp3, and this would have 4 sp3 orbitals, 4 single bonds, 109 degree bond angles, tetrahedral shape. 4 would be similar. If we went to 5, we see 3 bonds. So that means 4 minus 3 is 1. There must be 1 hydrogen here. Since there's a second bond, that has to be a pi bond using p orbitals. And so there would only be left s and 2 of the p's. 5 must be sp2 hybridized with trigonal planar shape and 120 degree bond angles. To have the 120 degree bond angles, we should have a hydrogen pointing straight up here. Okay? And so we could go through the rest of these. 7, you see 4 bonds. So 4 minus 4 is 0 hydrogens here. This is a little bit of a funny one. This is actually an sp carbon, but if I took that dot out of there, it would just look like a very, very long double bond carbon. So this implies that there's a carbon here, and there is a pi bond here on the left and a pi bond here on the right. And so this carbon would be sp. I see 4 bonds. 4 minus 4 is 0, so there are 0 hydrogens here. Down here at number 9, I see 2 bonds, so there must be 4 minus 2, there must be 2 hydrogens here. I see 1 pi bond with 9 using a p orbital, so this must be sp2 and trigonal planar shape and 120 degree bond angles. Okay, so if we come up here, First off, I see no pi bonds up here, so these are all sp3. If I want the number of hydrogens, I take the bonds that I see. For 11, that would be 2. 4 minus 2, there must be a CH2 here. If we look at number 12, I see 4 bonds. 4 minus 4 is 0. There are no hydrogens here. And finally, if I look at 14, I see 1 bond. 4 minus 1 is 3, so this must be a CH3. Okay? So you could try and answer these questions over here for every single carbon there. I put those answers here so that you can double check yourself as long as I filled in a table correctly. You might want to see if I made a mistake, so you can check yourself there. Now, the nice thing about this way of drawing structures is it works for all of the atoms that we talk about. So for the examples above with carbon, these are the 4 possibilities that I have shown up above. They all have 4 bonds. Okay? No lone pairs. Remember, the Z effective of carbon is +4. Its electronegativity is 2.5. So carbon, of the atoms that we work with, carbon, nitrogen, oxygen, and the halogens, carbon is the least electronegative. And so therefore, it's always going to be giving up a little bit of its electron density to its partners if they're nitrogen, oxygen, or fluorine. So, okay, so carbon can make 4 bonds, including this possibility here. Nitrogen can make 3 bonds, but now it's picked up an extra proton, so it has a higher Z effective, but it also has a lone pair for itself. So nitrogen is going to satisfy the octet rule, the noble gas configuration, with 3 bonds and a lone pair. But it can do this with all single bonds, or a double bond, single bond, okay, or a triple bond, and then a lone pair. Now nitrogen couldn't make 4 bonds without having formal charge, so I've left it out of this particular chart. Okay. If we go to oxygen, oxygen got an extra proton in the nucleus, so it's +6, and an extra electron in the valence shell. So oxygen only needs 2 electrons, and it does that satisfies that by getting paired up with somebody else with an electron, so it has 2 bonds, and 2 lone pairs. Since it could have 2 bonds, it could have a double bond, where the second bond is a pi bond, overlapping p orbitals, or it could be 2 single bonds. Okay. To go to 3 bonds is possible, but we would have to have formal charge. And since this is only neutral atoms, we're leaving that out. Okay? And oxygen has greater electronegativity, so of course it attracts electrons more to itself. If we go to fluorine, we get an extra proton in the nucleus, so now we're at +7 Z effective, and the valence electrons are 7 electrons. We only need 1 electron. We can do that with 1 bond. And then there's 3 lone pairs for fluorine. And this would work for chlorine, bromine, and iodine as well. We can't go to 2 bonds without making formal charge, so we left that one out. So again, fluorine is the most electronegative atom of the atoms that we use in organic chemistry. And finally, just hydrogen is a very important element, of course. It has a +1 Z effective. It has no shielding, no core electrons. The only electrons it has are its valence electrons, has 1. And it needs 1 electron to get the helium gas configuration. It cannot make 2 bonds. Okay? So here's a structure that has more than just carbon. It has nitrogen, oxygen, fluorine. And so when we have, these are called heteroatoms because they are different than carbon. And when we have heteroatoms, we actually write them in. So if I have an oxygen, I'm going to put an O and an O here. If I have a nitrogen, I'm going to put an N and an N and an N. If I have a halogen, I'll put the letter of the halogen, fluorine, chlorine, bromine, iodine. Okay, and if there is a hydrogen on the heteroatom, we write that as well. Okay, so this has a hydrogen. The nitrogen up here has a hydrogen, so we write that in. Usually, if you have an aldehyde, we write that hydrogen too. But not everybody does that. But most of the ones that I've seen do that. Okay, so now we could go around and do the same thing that we did up above. We could classify the hybridization of each of these. We could classify how many hydrogens are on each particular atom. The only ones that would really be hard would be the carbons. Okay, so as before, I see a second and third bond. So that means those are pi bonds involving p orbitals. All that's left is S and P, so this must be sp hybridized. 180-degree bond angles in linear shape. Okay, let's come down and take a look at an oxygen. Okay, here I have an oxygen with 2 single bonds, so there would also be 2 lone pairs that are not shown. Since there is no pi bond, this would be an sp3 oxygen. We would say 109-degree bond angles and tetrahedral shape. Okay, if I come up here and look at this carbon, I see 4 bonds. 4 minus 4 is 0, so there are no hydrogens on this. This, in fact, is a ketone. And if I look up at the oxygen, I see 2 bonds, so there would be 2 lone pairs. The hybridization would be determined by seeing that there's a second pi bond here. A second bond. And that uses p orbitals. So this would be sp2 hybridized. Lone pairs we would say are in sp2 orbital, hybrid orbitals at 120-degree angles. Okay, if we look at 7 is a carbon, because I don't have an atom. I see 3 bonds, 4 minus 3 is 1, so there would be 1 hydrogen. I see a second bond right here, that would be a pi bond using a p orbital. So this must be sp2, and there must be a hydrogen pointing straight down here. If we look at this nitrogen, I see 3 bonds, so there's a lone pair missing. Where would that be? Well, I see a pi bond here, that's a p orbital. So this would be sp2 hybridized, and 120-degree bond angles. In this case, the lone pair would be pointing straight down. Okay, if I come over and look at this nitrogen here, I see 3 bonds. There would be a lone pair that's not shown. The second and third bonds are pi bonds, and so those would be using p orbitals. This must be sp hybridized. The lone pair must be at 180 degrees opposite of 14, so a lone pair is sitting right here. This would be a nitrile group. If I come up here and look at this nitrogen, what I see are 3 bonds. Okay, so there are no pi bonds. This must be sp3 hybridized. There's a missing lone pair that could be put in next to the nitrogen. This nitrogen has 1 hydrogen, which we actually do show. Okay, and if we come up here and look at 18, 18 is a carbon. It has a pi bond, so this must be sp2 hybridized. In this case, this is an aldehyde, and we do write in the H. At least most of the books, and myself included, write in the H. Not everybody does that. This again would be an oxygen that is sp2 hybridized. Notice how it looks very similar to this oxygen down here. There would be 2 lone pairs in sp2 orbitals, 120 degrees. And if we follow on out here to the fluorine, we see 1 bond, which is what fluorine should have. There should be 3 lone pairs. Fluorine must be sp3 hybridized, and then we would put the 3 additional lone pairs around the fluorine here. Okay? And so you should be able to figure out every type of atom in a structure, even when it's written in this very condensed form. That makes it easier to write. I put all of those particular atoms and lone pairs and everything that you should be able to figure out here. You can check and see if I did that correctly or if I made any mistakes, or check for yourself too. Okay, so that's about it for this particular slide. Hopefully it will help you out with these bond line formulas.